Imagine a place in the universe where gravity is so intense, so utterly powerful, that not even light can escape its grasp. A place where space and time are warped beyond recognition. This is the mysterious realm of black holes, perhaps the most fascinating and terrifying entities in the cosmos. Black holes are not monsters lurking in space, devouring everything in their path without reason. They are the natural result of gravity and physics, born from the remnants of massive stars that have reached the end of their life cycle. When such a star exhausts its nuclear fuel, it can no longer resist the force of gravity. The core collapses in on itself, compressing matter to an unimaginably small point, a singularity surrounded by a boundary called the event horizon. Beyond this horizon, escape is impossible. But let's slow down. To understand black holes, we need to go back to Einstein. His general theory of relativity, published in 1915, described gravity not as a force, but as a curvature of space-time caused by mass and energy. The more massive an object, the more it bends the space around it. Black holes are the extreme version of this idea, points in space where the curvature becomes infinite. There are different kinds of black holes. The most common are stellar black holes, which form when stars many times the mass of our sun collapse. Then there are supermassive black holes which reside at the centers of galaxies, including our own, the Milky Way. These titans can contain millions or even billions of solar masses. How they formed remains a mystery, but we now know they play a key role in galaxy formation and evolution. There are also intermediate black holes, which may form from mergers of smaller black holes, and the theoretical primordial black holes, which could have formed just after the Big Bang. Though we haven't observed them directly, they remain a possibility in cosmological models. Now here's something astonishing. Black holes are not just cosmic vacuum cleaners. In fact, if our sun were replaced with a black hole of the same mass, Earth's orbit wouldn't change. We'd freeze without sunlight, yes, but we wouldn't be sucked in. That's because black holes only pull in matter that crosses the event horizon. Gravity works the same outside that region. Detecting black holes used to be nearly impossible. After all, how do you find something that doesn't emit light? The answer lies in observing their effects. When a black hole pulls in matter, like gas or even a nearby star, it heats that matter to incredible temperatures, often millions of degrees, emitting X-rays and gamma rays in the process. We've also observed stars orbiting invisible companions, their paths curving in ways that reveal the presence of massive, compact objects. This is how astronomers inferred the existence of the supermassive black hole at the center of our galaxy, Sagittarius, a star. In 2019, something remarkable happened. For the first time, humanity saw the unseeable. The Event Horizon Telescope, a planet-sized network of radio telescopes, captured the silhouette of a black hole in the galaxy M87, an orange glowing ring surrounding a dark core. This wasn't a photo in the traditional sense. It was a composite image built from complex data representing the shadow of the black hole as it bent and captured light. That image confirmed decades of theory and stunned the world. But the mysteries run deeper. At the heart of a black hole lies the singularity, a point where all known laws of physics break down. Density becomes infinite, and our equations simply stop working. This is where general relativity clashes with quantum mechanics, and it suggests that our understanding of the universe is still incomplete. This brings us to one of the most fascinating areas of physics today, black hole information paradox. In the 1970s, physicist Stephen Hawking proposed that black holes are not entirely black. Thanks to quantum effects near the event horizon, they emit a faint glow called Hawking radiation. Over vast timescales, this radiation could cause black holes to slowly evaporate. But here's the problem. If a black hole disappears, what happens to the information about the matter that fell into it? Quantum theory says information cannot be destroyed, yet black holes seem to do just that. This paradox has inspired decades of debate and countless theories, involving holograms, string theory, and quantum gravity. Some scientists now believe that information may be stored at the event horizon or subtly encoded in the Hawking radiation. Others suggest that our very idea of space-time may need to be rewritten. Beyond the science, black holes stir the imagination. They've become staples of science fiction, often portrayed as portals to other worlds, time machines, or gateways to alternate universes. And while many of these ideas are speculative, there is some basis in reality. The extreme warping of space-time near a black hole could, in theory, lead to effects like gravitational time dilation, where time slows down drastically near the event horizon. So in a sense, black holes are natural time machines, though not ones we could survive. In recent years, gravitational wave observatories like LIGO and Virgo have added another dimension to our understanding. These instruments detect ripples in the fabric of space-time caused by massive collisions, like the merger of two black holes. The first detection, in 2015, confirmed yet another prediction of Einstein's theory and opened a new era in astronomy. Now we can listen to the universe as well as see it. Black holes may be the universe's ultimate paradox: invisible, yet detectable; tiny, yet massive; simple in definition, yet infinitely complex in behavior. They stretch our understanding of physics, challenge our beliefs about space and time, and whisper secrets about the fundamental nature of reality. Perhaps most humbling of all is the realization that we are made of the same elements that once lit the cores of ancient stars. Stars that may have died in cataclysmic supernovae, leaving behind black holes that still roam the galaxy. In that sense, black holes are not just distant, exotic objects. They are part of the cosmic story to which we all belong. And though we may never touch one, never truly see beyond the event horizon, our minds can reach farther. They allow us to ask questions not just about what's out there, but about the very nature of existence. But even as we uncover more about black holes, new questions continue to emerge, some bordering on the philosophical. What happens to time and causality near the event horizon? Can two observers, one falling into a black hole and one watching from a distance, ever agree on what now means? These questions highlight how black holes challenge not just physics, but our fundamental concepts of reality itself. Take, for instance, the concept of spaghettification. It's a real scientific term that describes what would happen if you fell feet first into a stellar mass black hole. As you approach the event horizon, the difference in gravitational pull between your feet and your head becomes so extreme that your body would stretch like spaghetti. Eventually, you'd be torn apart, long before reaching the singularity. This terrifying process is called tidal disruption, and it's one of the many ways black holes demonstrate their raw, indifferent power. But the story is different for supermassive black holes, because their event horizons are so large and their gravitational gradients much weaker near the edge. You could, at least theoretically, cross the event horizon without immediately feeling anything. You might drift through, unaware that you've passed the point of no return. Of course, you'd still be doomed, but the ride would be eerily calm for a while. The difference in how these black holes behave has opened the door to one of the most intriguing theories in modern physics. Could black holes act as bridges or wormholes to other parts of the universe? These so-called Einstein-Rosen bridges are mathematical solutions to Einstein's equations, allowing for a tunnel through spacetime. The problem? They'd likely be unstable and collapse the moment any matter tried to pass through. Still, the idea tantalizes scientists and storytellers alike, because if we could somehow stabilize such a tunnel, it could revolutionize space travel and our understanding of the cosmos. Beyond theoretical speculation, black holes may also play a practical role in the future of space exploration. Their immense gravitational fields could, for example, be used to slingshot spacecraft at incredible speeds, using a technique called gravitational assist. And some theories suggest that the energy released by material spiraling into a black hole via accretion disks could be harnessed by advanced civilizations, providing a nearly limitless source of power. This leads into the concept of a Kardashev Type 2 or 3 civilization, capable of manipulating the energy of stars or even galaxies. It sounds like science fiction, but then again, so did black holes 100 years ago. There's also a growing body of research exploring whether black holes could hold clues about the origin of the universe itself.